So welcome back. And it's a pleasure to announce the next speaker. So it's Lucas Reis. He works at the Federal University of Minas Gerais. And he's going to talk about minimal value set polynomials over finite fields.
Okay. Can you hear me? Okay. So first, I would like to thank the organizers for the opportunity to give this presentation. And I will talk about a special class of polynomials over finite fields. And I'll briefly give a connection with algebraic curves over finite fields. So just to start with, fix Q is a prime power, and FQ denotes the finite field with Q elements. And now we consider F a polynomial over FQ of degree D. And we consider this set VF as the value set of F over FQ. So we just evaluate F at each element of FQ. And so from this basic observation, that if we take any element of FQ, alpha, and consider this equation, f of x equals alpha, we know that this has at most d distinct solutions over FQ. If d is the degree of f, we may deduce that the value set has cardinality at least q over d. So we just take the least integer greater than or equal to q over d. So I will just briefly explain the proof. It's quite simple. We observe that FQ is contained in the union of the pre-image of each element contained in the value set, right? So if it's not in the value set, this is empty, so we consider only the non-trivial sets. And if we take cardinality on both sides, right, we get that Q, cardinality of this set, is at most the union. So each set of this type has at most d distinct elements, so we get d times the cardinality of VF, right? So now we can get this bound. And so the natural question is when the polynomial attains, the value set attains this lower bound, right? We actually have the other extreme when it reaches the maximum value. It's a permutation polynomial, so the value set is the whole field. And so this is the other extreme when we have the this lower bound. And so in this case, we say that f is a minimal value set polynomial, MVSP, right? And so in this talk, we just discussed the natural problem of characterizing the MVSPs over finite fields. And so this study of this problem, characterizing MVSPs, started in the early 60s with works of Carlitz, Lewis, Mills, and Strauss on the description of these polynomials. And so I'll just emphasize the case where the value set has only one or two elements. This is a bit different from the other cases. And so, and actually we can describe all the polynomials whose value set is a MVSP with value set of cardinality 1 or 2. And so from now on, we only consider MVSPs with a value set having at least 3 elements. And so in particular, in these 2 papers, these authors just described the MVSPs over fields of size p and p squared. And so here's the description. Over FP, we only have up to affine equivalence. I will use this throughout the talk. So we are just like considering the polynomials up to pre and post compositions with affine maps. So we're just taking a change of variables to make simpler. And so over FP, we only have powers, x to the v, with v dividing p minus 1. And over FP square, we have x to the v, with v dividing p square minus 1. And 2 other families of polynomials. we have here x to the p plus x. This is just a trace function, fp squared over fp. And also this x to the p plus 1, which is just a norm function of fp squared over fp. And again, we can also take powers, v, where v is any divisor of p minus 1. Actually, there is also another family I just forgot to mention here, but it's not explicit as 1 and 2. It's just we consider finite field fq, and we have a subfield fbq. And so we just take a polynomial f of degree less than or equal to q minus 1 over bq minus 1, and the value set contained in the subfield. So he just observed that this always produces an MVSP, but it's not easy to determine explicitly the polynomials with this property. So now I'll just talk the connections with algebraic curves. So there's this paper from Storr and Volok. They just define what is a Q-Frobenius non-classical curve. If you take a polynomial in two variables, x and y, and you consider the related affine curve, f xy equals 0. This curve is called Q-Frobenius non-classical if the polynomial fxy divides this expression. So here's just a partial derivative with respect to x and y. And these curves are quite rare. Most of the curves won't have this property, but they have like many interesting properties. One of them is that they have potentially many rational points beyond some geometric properties. If I'm not wrong, you can deduce from this condition that we have this interesting geometric property. If you take the Q conjugate of a point on a curve, these 2 points determine the tangent line of the curve at this point P. And so there is a result from Erivelto just relating MVSPs and Frobenius non-classical curves. And so we take f and g to polynomials such that this separated polynomial is not in this subring, such that these two polynomials, they just give the image set over fq has cardinality at least 3. Then the irreducible components of this curve, f of x minus gy, the irreducible components are Q Frobenius non-classical if and only if f and g are MVSPs with the same value set. Okay, so back to minimal value set polynomials. The second paper is due to Mills in 1964. He just obtained an implicit description of MVSPs over all extensions of FP. In particular, as a very interesting corollary, he just described the MVSPs whose degree is at most the square root of the size of the field, excluding these ones that I just mentioned earlier. And so up to affine equivalence, changes of variables, the polynomials must be of this form, which is just a linearized polynomial. All the exponents are powers of the characteristic. And you just take L of x to the power of v. And we just ask this polynomial L, this linearized polynomial, to split completely over fq. And we have also some arithmetic conditions. I'm not going into that. And so there's only one point here that this is not quite explicit. We're just asking we just want this polynomial to split completely. But the point is that this is by itself an open problem, whether a linearized polynomial splits completely. We just know when this is a binomial, some partial results from trinomials, and 4 or more non-zero coefficients, it's widely open. And an interesting point here is that this family does not generate many MVSPs. So up to affine equivalence, we only have one of these if we prescribe the value set. And so in the same paper, it was not a conjecture, he just like a kind of strong guess, you know, that this will probably extend to the other range when you consider the degree large, right? And so here's the statement of just like, I'm just compiling many informations from used papers, who just gave this implicit description of MVSPs over general fields, right? Here, this is not the exact statement. I'm assuming that I'm taking an MVSP and 0 is in the value set and is the element with the least pre-image, right? So 0 is in the value set, and if you take A equals 0, this is the set of least cardinality. We can always assume there after change of variables. And so in this case, we have some information on F. It must be of this form, power of L. L is just the polynomial collecting all the roots of my original polynomial in FQ. So we also have a polynomial N here. We do not have much information on N. And the important thing here is the information on the value set itself. So if you take Tx is just the vanishing polynomial of the value set. It has this form, right? So it must be of this form. So it's close to a linearized if you take a composition. And the most important thing, in my opinion, is this functional equation it gives. So if you take the vanishing polynomial of the value set and compose with F, you just get a constant theta times x to the q minus x times the derivative of F. And so from the third item, we actually can conclude that that the value set cannot be anything, right? So if you take an MVSP, the value set must be of this form. You just take u to the v when u runs over the elements of an FQ vector space of the algebraic closure of FQ, right? So the value set is somehow special. And more recently, in 2013, Borges and Conceição, they obtained a complete description of MVSPs when the value set is a subfield, right? So we're now just changing things. We've prescribed the value set and ask where are the MVSPs with this value set. So in that paper, the key idea is to explore this functional equation, which is given for general MVSPs. And this is really interesting because when the value set is a subfield, the polynomial T has a special form, is of this form, x to the bq minus x. And this is again a linearized polynomial. So this functional equation becomes a linear equation. And so in particular, the set of solutions, f here is the variable, right? We're trying to find f given t. And this will be a linear equation. So it's essentially the set of solutions is a vector space. And basically, they just gave a full description of this vector space. Also, another interesting thing they just obtained is that this class of these weird polynomials, he just conjectured that all of them will be of this form, right? Apart from the first part, powers of linearized, we just have polynomials arising from this construction. And so we have this inequality, right? So the degree must be, at most, this expression. And so in that paper, they just obtained some MVSPs having this property, that the value set falls in a subfield, but this is not satisfied. The degree is greater than this quotient. And so this kind of indicated that the description cannot be that simple. And if you observe, I'm just like highlighting the advances on this problem. It just started like 62, and we have this result from 2013. So almost 50 years, we do not have much to say. And so the main result we just obtained is a paper from 2021. We were able to characterize the MVSPs over fields of size p cubed. And so here's the description We have 3 families of polynomials. The first 2 were already expected from general cases. And I'm just focusing on the third one. We just take G is an IMVSP over FP cubed with value set FP. So the value set is a subfield, and you take powers. And here's the description of all G's, possible G's. We have a nice expression for them. And this was only possible because we have in 2013 a full characterization of MVSPs whose value set is a subfield, right? So we get the explicit form of these polynomials. And so as an application, it's not too straightforward, but if we consider curves of this type, y to the n equals f of x, to ones that are p cube Frobenius non-classical were classified in this paper when n is at least p cubed minus 1. And so from our main theorem, we were able to classify the remaining cases. So if n is at most is smaller than p cubed minus 1, we necessarily have the n is p squared plus p plus 1, and f must be an MVSP whose value set is exactly the subfield FP. Okay. So I'll just briefly comment on the proof of the classification of MVSPs over FP cube. We essentially consider many possible situations for the value set, and the hardest one, I would just comment on the hardest one, is when the value set is a cyclic group union with a 0. This is the hardest one. We just go back to the functional equation. T will be really nice. We get this equation. And basically, we combine the main theorem from Mills. The theorem from Mills just gives f in terms of 3 other polynomials. So we just substitute everything in this equation. We get a simpler equation, but now 3 polynomials as variables, right? And so we just had to be smart and we use something, things very strange like ABC theorem for polynomials. And, but unfortunately, we are not able to extend this technique for larger fields. The point is just that the degrees of these 3 polynomials cannot be controlled very well. And we are only able to do it for p cubed because there's no much space for the possible degrees of these 3 polynomials. And so just to finish, I'll just comment on some work in progress with Erivelto. We just need to finish the paper. Most of the things are done. And so the first result is we actually improved the first corollary from Mills' paper. First, we only had that the value set is u to the v with the vector space being in the algebraic closure of FQ. Now we can prove that, we are able to prove that the vector space is actually inside FQ. And the converse is also true. If I take a vector space inside FQ and take a power, we can find MVSPs with this value set. So we basically describe all the possible admissible value sets of an MVSP over finite fields. Well, the second result is actually just an extension. In 2013, they just considered the case where the value set is a subfield. Now we have a more general thing. Basically, any vector subspace is, of course, subfields are particular cases of vector subspaces. And in fact, in 2013, Erivelto and Ricardo, they just gave a guess about the description in this case, but they were not able to prove that this was actually the family. There are some computations, but computations in this problem is quite hard. Because there are many, many variables, and the number of possibilities grows exponentially. So this was just more like to see if we can find a counterexample. But of course, it's not, because it's true. The family, they just provided this, the full description. And finally, this is very, very recent. From the first improvement in one, that the vector space actually is in FQ, not in the algebraic closure. We are able to combine our techniques in FP cube to obtain a solution for P4. So, and the interesting part is that the new ingredient is Weyls bound for the number of rational points on algebraic curves. So basically, we tried to do this before, but we could not control the rational points because they could be in the algebraic closure. So if they are in a very large extension, we cannot say anything. But now we know that it is in FQ. OK. So these are the references, and I'm done. Thank you.